Hello, I'm Mike McCulloch. So I thought I'd bring you to this Devon field to try and explain something about how to use quantized inertia to quantum launch up straight to orbit. Now, from an engineering standpoint, I don't fully know how to do this yet, but the theory of quantized inertia suggests certain pathways that we can take. So one way to do it would be as shown here in schematic form, rough schematic form. So we have a battery, and the lightest and most efficient battery, well, that I know about, is a lithium polymer battery, which can produce about 15 volts from about 0.3 kilogram weight. So that's the box at the bottom. And then we would need to take that small voltage and convert it to a larger voltage with a transformer, which might be about 0.1 kilograms, and that's shown by the box above it. Then things like flyback controllers and switches apply that voltage to capacitors, but it doesn't necessarily have to be capacitors. It could be any structure that encourages electrons to jump rapidly across a gap, and potentially also asymmetric, so metal structures that are asymmetric that produce that sort of thing. So the total weight of this thing might be something like 0.7 kilograms. So in order to lift it off the ground, we would need 7 newtons. The advantage with this is that the battery is enclosed, it's all self-contained, so if it does lift off, it'll continue to lift off. So how the crucial factor here is that quantized inertia predicts that if you have a capacitor or an asymmetric structure with electrons accelerating very rapidly inside them, then they will produce force, but the force increases very strongly with a decrease in the separation between the capacitor plates or the size of the other structures. And we can write down a formula, which is shown here, showing the force predicted by quantized inertia based on the current that's flowing across the gap, the area of the capacitor or other structure, divided by d squared, where d is the separation between the plates or the size of the cavity that we're using. So this is very if you put the values in here for the charge on the electron and the mass of the electron, you get this formula, and then we can rearrange this to work out what capacitor separation or cavity size we need to produce 7 newtons, and that says that D is root I over 2236 or thereabout, which means that for a feasible current of about 0.1 microamp, we would need about 1 microamp. We would need something like a cavity size or a plate separation of 0.4 micrometers, which is not impossible given the technology we have, but there are still. So this is theoretically what you would need to do. This does not guarantee that, of course, it works from an engineering standpoint, because there are many other things which get in the way of that. Failure of equipment, electrons sparking across the gap instead of tunneling across the gap as they're supposed to in quantized inertia. That's what we want them to do. We want them to tunnel. But this gives us at least some kind of a rough idea about what to do, and how someday it might be a Devon field like this that we would see a small quantized inertia craft lifting off. Okay, so I hope you've enjoyed this short and it's stimulated some thoughts, and I look forward to speaking to you next time. Okay, goodbye.